Imagine staring into the silent darkness of space, only to realize something out there is staring back. In July 2025, a telescope 1.5 million kilometers from Earth captured an image that would redefine what we think we know about the universe. The James Webb Space Telescope, humanity's most advanced eye on the cosmos, recorded the first real spectral image of an interstellar visitor called 3I Atlas, and what it revealed shook even the most skeptical astronomers. This was not another blurry light dot in a telescope frame. This was a chemically rich, fully mapped portrait of an object that did not come from our solar system. Every pixel told a story from a different star. The discovery marked a turning point in modern astronomy, not just because we finally caught one of these wanderers in extraordinary detail, but because the data exposed something profoundly alien about its nature. Detected on July 1, 2025 by the Atlas monitoring system in Hawaii, 3I Atlas became the third confirmed interstellar object after Oumuamua and Borisov. But unlike its predecessors, one too dry and geometric, the other too familiar and icy, this one offered direct high-resolution data that could not be dismissed as coincidence or error. On August 6, 2025, Webb's NIRSpec instrument, near-infrared spectrograph, locked onto a faint moving target, an almost impossible task requiring hours of coordinated calibration. What emerged from the deep sky data wasn't just an image. It was a multidimensional chemical fingerprint. The results? A coma or gas cloud dominated by carbon dioxide emitting infrared light between 0.6 and 5.3 micrometers. That's where the shock began. The CO2-to-water ratio was approximately 8:1, of the highest ever recorded in a comet, 8 times more carbon dioxide than water vapor. This wasn't just a minor anomaly. It was a sign that 3I Atlas formed in an environment colder and more remote than any region we've studied within our solar system. Typical comets from our cosmic neighborhood heat up near the sun, releasing mostly water vapor. But Atlas, shielded by thick insulating layers, didn't follow the script. Instead, it released only the most volatile gases, carbon dioxide and carbon monoxide, suggesting that beneath its crust, frozen reserves of ancient materials were locked away, untouched for billions of years. When Webb turned its gaze toward this drifting relic, it didn't just see a visitor, it saw a messenger from another world carrying the chemistry of an alien sunrise. Scientists studying the data noted that gas was escaping more intensely from the sunlit side, creating a wide, diffuse plume rather than narrow jets. That asymmetry hinted at internal fractures and uneven sublimation zones, evidence of a body shaped by violent forces and deep thermal scars. Each pixel became a data point, and each wavelength a whisper from a distant past. A story about how planets and comets form under stars. We'll never see with the naked eye. But here's where the mystery deepens. If 3I Atlas truly came from beyond the sun's gravitational reach, what could its composition tell us about the birthplaces of other planetary systems? Could it mean that carbon dioxide-dominated comets are the norm elsewhere, and Earth's water-rich world? The true anomaly. One picture suddenly opened 1,000 questions, and for the first time we had more than light. We had substance, structure, and memory embedded in a rock that had traveled for billions of years through interstellar night. What James Webb captured wasn't just an image. It was a cosmic confession. The deeper scientists analyzed the Webb data, the stranger 3I Atlas became. Its chemical spectrum read like a relic from a forgotten system, heavy in carbon dioxide streaked with traces of carbon monoxide, faint water vapor, metallic nickel, and even molecules like OCS, a compound rarely found in our local comets. Each spectral line revealed that this wasn't a product of the same solar nursery that shaped our planets. It was a fossil from a region so cold and so far from any star that water itself might have frozen before ever forming into ice crystals. Webb's NIRSpec didn't just capture a glow, it mapped a living chemistry, a dynamic reaction between sunlight and ancient frozen gas. The comet's activity pattern defied logic, while ordinary comets wake up near Jupiter's orbit. Atlas was already venting gas far beyond that distance, as if it carried its own internal trigger. The explanation, according to early modeling from ESA and NASA teams, might lie in its highly porous structure. Deep inside, volatile ices such as CO2 and CO could react to even slight temperature changes, creating pressure pockets that burst open long before sunlight could melt water ice. These eruptions, faint but steady, produced a coma that was thick yet diffuse, bright enough for Webb to trace its exact geometry. The result was not a single focused tail, but a broad emission field, an enormous uneven halo that wrapped around the core like a shroud. And in that haze, Webb detected faint hints of nickel dust, a material forged only in the intense heat of massive stars or supernovae. How could something born in such cold contain traces of such fire? The answer may rest in cosmic violence. 3I Atlas, some researchers suggest, could have formed in a disk enriched by stellar explosions, a mix of frozen gases and metallic ash from a star's death. That would make it one of the oldest mixed remnants ever observed, possibly predating the Sun by billions of years. Even its movement through space reinforced the sense of strangeness. Traveling at nearly 210,000 kilometers per hour, Atlas is one of the fastest natural objects ever tracked, moving along a hyperbolic trajectory that ensures it will never return. Models indicate it may have been ejected from the dense Sagittarius arm of our galaxy, thrown out by the gravitational chaos of giant planets or passing stars. Every part of its journey, its chemical balance, its path, its quiet defiance of solar heat suggests we're witnessing not just a comet, but a survivor of cosmic catastrophe. And yet, even in its clarity, the image Webb produced hides more than it reveals. The core itself remains invisible, drowned in the glow of the surrounding coma. We can measure its mass, roughly 3 times 10 to the power of 10 metric tons, and estimate its size between 1 and 5.5 kilometers across. But we still don't know what it looks like inside. Beneath that cloud of sublimating gas might lie cracks, voids, or even stratified layers of exotic ice unknown on Earth. Each hypothesis opens another door, and every answer raises more unsettling questions about how matter evolves in the deep galactic cold. By September 2025, the scientific community was in open debate. The Webb images and spectral data had leaked into academic circles, and the conclusions didn't all agree. Some teams claimed 3I Atlas was simply an unusually cold comet preserved in a distant orbit before being knocked into interstellar space. Others argued that the high CO2 ratio and metallic traces pointed to a much more exotic origin, possibly a fragment from the outer disk of a red dwarf system, or even the ejected remains of a destroyed exoplanet's atmosphere. The European Space Agency's Near-Earth Object Coordination Center described the data as chemically unprecedented, while NASA's Deep Space Analysis Division emphasized how stable the object appeared despite its violent outgassing. Stability and chaos coexisting, that paradox made 3I Atlas a mystery. When scientists compared it to Oumuamua and Borisov, its uniqueness became even clearer. Oumuamua had reflected sunlight, but emitted no detectable gases, leading to wild speculation about artificial propulsion. Borisov, in contrast, behaved like a typical comet, icy, predictable, familiar. But Atlas was neither. It glowed with its own internal pattern, pulsing faintly in infrared intervals that repeated like a slow heartbeat, a rhythm so consistent that Webb operators initially thought their instruments were malfunctioning. It wasn't noise. It was real. This rhythmic emission was later linked to the comet's rotation, but the precision of the pattern raised an unnerving thought. How could such mathematical regularity emerge in something natural? No one dared to say artificial, but the word hung in the air like static. The phenomenon also exposed the limits of Earth-based telescopes. Even the Hubble, trapped within the blur of our atmosphere, could not isolate the faint variations Webb picked up in the vacuum of deep space. And that's where the story turned from astronomy into philosophy. For the first time, humans were looking at something that had crossed light years, untouched its atoms, still remembering a star that may no longer exist. It wasn't just data. It was a message written in the universal language of chemistry. The implications stretched beyond curiosity. If such CO2-dominant bodies are common beyond our system, then carbon-based chemistry, perhaps even life, could thrive in environments we once thought sterile. The so-called cold worlds might not be lifeless at all, but merely dormant, their activity waiting to ignite when warmth returns. In this sense, 3I Atlas became more than a scientific specimen. It was a mirror held up to our assumptions about life itself. Could it be that what we call rare is actually typical, and our water-rich Earth is the cosmic exception? The question haunted every researcher who stared at those Webb datasets at 3 a.m., seeing in those infrared lines not a comet but a possibility. As October 2025 approached, 3I Atlas neared its closest point to the Sun, roughly within Mars's orbit, and the tension in observatories around the world grew. The comet's activity spiked dramatically, its tail expanding into a luminous arc that stretched millions of kilometers, glowing brighter than predicted even in infrared wavelengths. For a brief moment, before it slipped behind the Sun, ground-based observatories like Gemini South and the Very Large Telescope managed to capture complementary images confirming Webb's earlier findings. The comet's brightness didn't fluctuate randomly. It pulsed. The pattern, once every 16 hours, matched perfectly across instruments, suggesting a stable rotational rhythm. But the more stable it appeared, the stranger it seemed. How could a body losing thousands of tons of gas per second remain so perfectly balanced? Models simulated by the Jet Propulsion Laboratory proposed that the comet's rigid internal structure, perhaps a dense metallic core wrapped in porous ice, acted as a stabilizing counterweight, allowing it to spin evenly despite immense gas pressure. If true, it would mean 3I Atlas was unlike any comet ever studied, a hybrid of stone and frost forged in alien conditions. And yet, even as the science became clearer, public speculation erupted. Some commentators drew parallels to Oumuamua, hinting at engineered symmetry. Others pointed to the object's extreme age, estimated between 3 and 11 billion years, and wondered aloud whether such longevity was even possible for something unprotected drifting through radiation-filled interstellar space. What kind of material could endure that long without disintegrating? Astrophysicists offered rational answers: dense molecular bonds, nickel reinforcement, low erosion due to minimal collisions, but the fascination had already escaped academic boundaries. In countless online forums and late-night discussions, 3I Atlas transformed from a comet into a symbol, a reminder that the universe still keeps secrets far beyond our predictive power. When Webb's final dataset of the comet was transmitted before solar occlusion, it contained microscopic variations in light scatter that some researchers believe may reveal layered structures beneath the surface, perhaps fossilized strata of ice dust and metal deposited over eons of galactic wandering. If confirmed, that would make 3I Atlas not only the oldest known traveler, but also a geological archive of multiple star systems, a cosmic time capsule carrying the fingerprints of lost worlds. Soon it will vanish again into the dark, accelerating away from the Sun at impossible speed, never to return. But the information it left behind, every atom, every photon, will be analyzed for decades, reshaping how we think about the origins of life and the chemistry of creation itself. And perhaps the real question is no longer where 3I Atlas came from, but how many more like it are still out there silently crossing the void, carrying the forgotten memories of stars that died before ours was even born.